Today I'm going to show how steps minimize dissipation in rapidly driven stochastic systems. We are going to begin with an introduction to stochastic thermodynamics, starting with classical thermodynamics, which typically describes transformations of work, heat, and entropy. The type of systems we have in mind are, for example, this piston driven by hot and cold reservoirs to drive this crankshaft. The birth of thermodynamics as a modern science is widely regarded as starting in 1824, when Carnot released his book Reflections on the Motive Power of Fire. In this book, he described the efficient operation of heat engines. The description of very efficiently driving these engines has remained a central theme in thermodynamics even today, and has led to very important discoveries. For example, it describes quasi-static and adiabatic protocols. It has led to things like the Clausius inequality, which is a statement of the second law, and states that when you drive a system, the amount of work that you do is always greater than or equal to the free energy difference. It also led to very important discoveries like the Carnot cycle, which puts an upper bound on the efficiency of a heat engine. In stochastic thermodynamics, rather than describing these macroscopic heat engines, typically what we want to describe are microscopic machines. So in this animation, I'm showing ATP synthase, which lives in the mitochondrial membrane, and is a molecular motor that drives a central crankshaft and synthesizes ATP. Now, once again, we want to describe transformations of work, heat, and entropy. However, now for these micro and nanoscale stochastic fluctuating systems. So just from looking at this animation, you can see that this type of molecular motor is very different from the classical system. So these particles are bouncing and fluctuating around, and any realization of any given protocol is going to be different. So one result of this is that the Clausius inequality is actually only valid on average. So if you watch this animation, or if you watch ATP synthase, what you'd find is that for any single rotation around, the work that you do is not always greater than or equal to the free energy difference, which seems like a violation of the second law of thermodynamics. However, for these microscopic fluctuating systems, the second law is actually only valid on average, so it's only after many, many realizations, after it rotates around many, many times, that you recover the second law and the Clausius inequality. So these microscopic engines actually live in a world that's very different from these macroscopic engines that we're typically familiar with. Now what we want to do is follow a similar line of inquiry as Carnot and look for the efficient operation of these machines. In particular, we already have a reasonably good understanding of efficient flow control, and here's just one reference on how our group thinks about this. However, we know considerably less about fast control, and that's what I'm going to be discussing today. So to set up the problem, we're going to be looking at optimal control. And our goal is to perform a task, which we call a control protocol, at minimum energetic cost. So we have in mind some general control parameter space. We want to go from some initial control parameter to some final control parameter. Now to go from one point to the other, you can follow any path through control parameter space, but each different path will differ in its energetic cost. Now our goal will define the path that has the minimum energetic cost. The type of systems we have in mind are, for example, a Brownian particle trapped in a harmonic potential where you move the center of the trap or you change the stiffness of the trap. So this system can actually be realized experimentally by optical tweezers trapping a micron-sized bead. You can move the trap by moving the foci of the lasers, and you can change the stiffness by changing the intensity of the laser trap. Now in terms of results, like I mentioned before, we're going to be looking at the fast limit. So we have a fast protocol approximation. The quantity that we're going to be looking at is known as the saved work. So what the saved work is how much work you saved compared to an instantaneous protocol. So the instantaneous protocol is one where you start from your initial state and you instantaneously change to the final state. So it's an infinitely fast protocol. What the saved work quantifies is by going a little bit slower than this, how much work do you save by allowing yourself some time to relax towards equilibrium. So in particular, we have an approximation for this saved work in terms of two terms. So this first one is the initial force relaxation rate, which describes how quickly you relax towards equilibrium. And this second term is the control parameter distance. It sort of quantifies how far are you going. Now our goal now is to maximize the saved work and hence have the maximum energetic efficiency. So it turns out to maximize this quantity is very easy. So we want to find the control parameter protocol, lambda of t, which maximizes this. And because there's no velocities or accelerations in here, the maximum is just given by a single value. So what this implies is that the optimal protocol starts from your initial control parameter value, jumps to some intermediate optimal value, sits there for the entire duration, and then jumps at the end. And that's the protocol that will maximize this saved work in the fast limit. For this one specific model system of this Brownian particle in the harmonic potential where we change the stiffness, we can get a bit better of an idea for the energetics. So in particular, I'm going to plot the force as a function of control parameter. And if you think back to your undergraduate definition of work as being force times distance, here it's very similar. Work on this will be given by force times the control parameter distance. So it will be given by the area under the curve on these graphs. So we start from some initial point in control parameter space, and we want to go to some final point. Now if we did this infinitely slowly and continuously, the work that you would do in going from one to the other is given by the free energy difference. And then when you go backwards, so we open the trap and then we close the trap, if you once again do it continuously and infinitely slowly, you get all of this work back and you don't waste any energy. However, this would take infinitely long. So in the opposite limit, the very fast limit of an instantaneous protocol, you start from your initial control parameter value, jump to your final control parameter value without relaxing at all. And then finally at the end of the protocol, that's when you relax towards equilibrium. And then by doing this, you do an additional work larger than the free energy difference given by this red rectangle here. And then when you go backwards, you get some of this work back. However, the instantaneous work that you do in this entire cycle is still given by this red rectangle. So you've wasted a lot of energy by doing this really, really fast. If you allow yourself some short amount of time to relax towards equilibrium and follow this optimal protocol that I've described, then the protocol would look something like this. So you jump to some intermediate value, you relax towards equilibrium, and then you jump at the end. And then finally, to go backwards, you relax towards equilibrium, do this whole process in reverse, relax for a short amount of time, jump towards the end, and jump again. So the area of this green rectangle gives the saved work. And our goal is to maximize this saved work. So the height of this rectangle is determined by this initial force relaxation rate. It determines how quickly you relax towards equilibrium. The width of this rectangle is determined by this control parameter distance. Now what we do in these optimal protocols is we maximize the area of this rectangle, and it turns out this is optimized by this discrete jump protocol, where you jump from your initial value to some intermediate one, relax for the entire duration, and then jump at the end. Now finally, I would just like to emphasize that this result, although I just showed it for one simple model system, is actually very general. So for most stochastic systems, you can show that what we call the short time efficient protocol, or STEP, is actually optimal in the fast limit. So just a few examples that I've shown here is the Ising model. We apply different magnetic fields to different spins in order to flip them from spin down to spin up. We also show the Brownian particle in a harmonic potential where we move the center of the trap, as well as where we move the stiffness of the trap. For all of these systems, as well as many, many more, the short time efficient protocol, that is the optimal protocol in the fast limit, is given by these steps. So this just goes to show by looking at approximations in the fast protocol limit, we can find very general, universal design principles that govern how to operate these microscopic stochastic machines maximally efficiently. This has greatly improved our understanding of the efficient control of stochastic engines.